Hey, we're going to look at logarithmic functions today. So first off, let's talk about how we convert from exponential to log form. I use this to help me remember that we switch from Ben to Benny form. They're alter egos. Okay, so Ben is base to an exponent. Base to an exponent equals a number. So like this, 4 to the x equals 16. And then to switch into its logarithmic counterpart, we use log base, same base, of the number equals the exponent. So the number and the exponent switch. So we're going to get in log form, we get log, the base is 4, the exponent is x, so that equals our exponent, and the number it equals is 16. That's how I remember that. Ben and Benny. Another way we can do this is like this. We can go use the snail method. So you start with the base, move to the number, and then the exponent. So when I write this in logarithmic form, the number to the number equals the exponent. If I want to change back from logarithmic form to exponential form, I go the number to the exponent, the base to the exponent equals the number. All right, the next one. We're going to look at these 4 properties. So, and then we'll do a bunch more properties tomorrow. So, the first one, if you have log base a of 1, remember if I change that into exponential form, I can be like a to the something is equal to 1. And so that's always the power of 0. Logarithms are just powers. They're the powers of the exponential. Okay. The next one, so I'm going to change it. A to the something is equal to the number a to the x. So that's how we prove that one. So if I have a to the log base a of x is equal to x, this is, again, we're going to do log base a of x is equal to the exponent log base a of x. So we know those are true. Okay. The next one, log base a of a to the something is equal to a. That's to the 1 power. The 1-to-1 property is if log base a of x is equal to log base a of y, then we know that we can drop really what we're comparing are the numbers, so x is equal to y. Okay, it's called the 1-to-1 property. So the next ones, we're going to simplify log base 5 of 5 to the x power. We're going to look at our properties. That looks like this one. So I know that this is equal to, basically log base 5 of 5 just cancels to give me x. Or I can switch it and be like x to the 5 to the something is equal to 5 to the x. So using my 1-to-1 property, I can know that the question mark is equal to x. Okay. So again, the second one is using our inverse property. Sorry, this is inverse. This is also our inverse property. So we can see that if you have a base to the log of the same base, then this is just going to equal the input of the log, so 14. Again, we can say if this was a question mark, log base 7 of question mark is equal to log base 7 of 14. So the question mark is equal to 14. Okay. Next, log base 4 of 4, x is equal to 1. This one, log base 2 of x is equal to log base 2 of 3. So we're just matching our inputs. So x is equal to 3. This is the 1-to-1 property. That's this. 1-to-1. Okay. All right, graphing logarithms. I have sketched a graph for you. So you can see that the domain is when x, this little x with the line means the set of x's. So the set of x's is x has to be greater than 0. And the y's are all real numbers. Okay. The asymptote is, since this is the inverse of an exponential, and we're not going to be at y equals 0, we're now going to be at x equals 0. The function is always increasing, and all mother functions of a log intersect at 1, 0. Just like the inverse of an exponential function's intersection is 0, 1. So remember, logs for mother functions have all different mother functions depending on the base. So log base 2 of x, log base 3 of x. These are all different mother functions. Okay. Another mother function that we're going to see a lot is this one, the natural logarithm. So remember, e to the x is special. Find the buttons on your calculator again. Okay. So think about how you would use your properties of logarithms to solve e to the x is equal to 10. Well, we can convert it into log base, so snail or Ben or Benny. So the base is e, the number is 10 is equal to x. So how would I do this in my calculator? You would write the ln of 10. Okay, the ln of 10 is equal to x. So log base e of x is equal to the ln of x. So built into this, built into ln is basically the base e. So we don't ever write log base e like this. We write it as the ln of x. Okay. So next, we're going to create a table for e to the x and ln of x. I went ahead and already graphed e to the x for you because we did it in our last notes. So let's get the values for the ln of x. What is the relationship between e to the x and ln of x? They are, if you compose them, they are inverses. Okay, so ln of negative 2, I got an error. ln of negative 1, error. Or undefined. You write undefined. Be better. Undefined. 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 Ln of 1 is 0. Ln of 2 is 0.693. And ln of 3 is 1.098. I went ahead and just used my calculator. All right, we're going to graph this in blue. So I can see that I have a vertical asymptote here at 0. I have an x-intercept at 1, 0. And then at 2, we go up about a little more than half and a little bit more than 1. So this is slowly increasing. This. At 2.7, we'll be at 1 because that's the value of e. Okay. So those are our features. That's what our logarithm graph looks like. Our natural logarithm graph looks like. It looks like all other logarithm graphs, but it's a little trickier to plot your points because our base is already an irrational number. Okay. All right, so transformations. We're going to look at ln of x. Remember, we don't really write it as log base e of x. We're going to just state the transformation and state the new domain. So we have ln of x minus 2 is going to go to the right 2. So the graph started here, and if it moves to the right 2, the asymptote is going to move to the right too. So x has to be greater than 2. So the asymptote moves as well. Okay, the next one, we're going to move left 2. So that means the asymptote moves. The asymptote moves left 2. And the graph looks like that. Okay, so x has to be greater than negative 2. This next one, we're moving up 3. So the asymptote is staying at 0, but the graph is going to move up. Okay, so the domain stays the same. X has to be greater than 0. This next one, ln of x, negative ln of x, this is a vertical reflect over the x-axis, since we've been struggling with that. Okay, so the original looks like this. And so the new reflection is going to reflect over the x-axis. Does that change the domain? Nope. So x has to be greater than 0. All right, the next one is going to horizontally reflect. Horizontal reflect over the y-axis. So I start with my original. It goes like that. Okay. Horizontal reflection over the y-axis. So instead of crossing at 1, 0, we're going to cross at negative 1, 0. And then the graph looks something like that. So does that change our domain? Well, yes, it does. We're only on the left side of the graph. So x has to be less than 0. Okay. Then again, for our transformations of functions, we're going to go ahead and use our same variables from exponentials. So we have a times, or parameters, excuse me, a times log base b of d times x minus h plus k. And guess what? All those parameters do the exact same thing to our logarithmic function, except for, I see a mistake here. No longer is the k value going to be our horizontal asymptote. So what is going to change is our h value. Our h value tells us where our vertical asymptote is. So it tells us where vertical asymptote is. So x is going to equal h. All right, for our vertical asymptote. And that's it for now.